Step outside at midnight in an eternal universe evenly filled with stars, and the darkness above you should not exist. That sounds wrong. Night is supposed to be dark. The sun has gone below the horizon. The stars are far away, and most of space appears empty. Problem solved. Except it is not. If the universe had existed forever, remained static, and contained stars spread evenly through endless space, then almost every direction you looked should eventually end on a luminous surface. Midnight would not be black. It would approach the brightness of a sky covered by stars. So the real question is not why the sun disappears at night, it is why the space between the stars stays dark at all. Our first instinct is distance. A nearby star can be bright. A distant star becomes faint. Put enough distance between us and the rest of the universe, and surely the light must fade into nothing. That idea feels safe, until we build the universe around us one shell at a time. Picture yourself at the center of a gigantic spherical stadium. The first row contains lamps. The next row is farther away, so each lamp looks dimmer. Double the distance, and each identical lamp gives you only about 1/4 of the brightness. Good, darkness seems to be winning. But the farther row is also much larger. It has room for roughly 4 times as many lamps. Each lamp contributes 1/4 of the light, but there are about 4 times as many lamps. The loss and the gain cancel. Add another show, then another. Under the idealized assumptions of a static, uniform universe, each populated shell can contribute a comparable amount of total light. Distance weakens every individual star, but the growing number of stars prevents the total contribution from fading away. This is the mathematical trap inside Olbers Paradox. Heinrich Wilhelm Olbers gave the problem its modern name through his 1826 formulation. The uncomfortable point was simple in an eternal, static, stellar universe. Darkness should not survive. Maybe stars are simply too small, and the gaps between them are real. We can look between the lamps. But imagine an endless, sufficiently dense forest. Nearby trunks leave visible openings. Look farther through those openings, and eventually another trunk stands in the way. Give the forest unlimited depth, and the gaps disappear. The analogy does not mean stars literally touch like trees. It shows what unlimited line of sight depth does. If the old assumptions were true, extending your gaze through enough populated shells would eventually place a luminous surface in almost every direction. So empty-looking gaps do not rescue an infinitely old, uniformly luminous cosmos. Then we reach for dust. That sounds more promising. Space contains gas and dust. Dust can absorb visible light, scatter it, and hide stars behind dark clouds. Perhaps the missing light is still there, blocked before it reaches us. For real regions of the sky, dust absolutely matters. It can remove light from one direction and shift energy from one wavelength to another. But in an eternal equilibrium universe, it cannot act like a bottomless trash can for radiation. Put a curtain in front of a heater. The curtain blocks the direct glow, but it absorbs energy, becomes warm, and releases that energy into the room. It changes how the energy reaches you. It does not make the energy vanish. Cosmic dust behaves differently in detail, but the energy problem remains. Absorbed radiation heats the material and is eventually re-radiated or redistributed, often toward longer wavelengths. Dust can hide visible light. It cannot permanently erase unlimited energy arriving for unlimited time. In 1964, physicist and cosmologist Edward R. Harrison gave the paradox a modern physical treatment. Later, James M. Overduin and Paul S. Wesson quantified the roles of cosmic light production time and expansion. Their work points toward the assumption that truly fails. The universe has not been shining forever. The universe appears to be about 13.8 billion years old. That does not mean the entire universe must be only 13.8 billion light years across. Age is a duration, not a ruler placed across all of space. The universe may extend far beyond the region we can observe, and it may even be spatially infinite. But light has still had only a finite time to travel. Return to the spherical stadium. The rows may continue beyond anything we can see, but now place a cosmic clock beside them. The lamps have not been on forever. Light from sufficiently distant rows has not had enough time to reach you. The endless sequence of equally contributing luminous shells is cut off. Even that gives the classical paradox too much light-producing time. Stars and galaxies did not begin shining at the first instant of cosmic history. For hundreds of millions of years after the Big Bang, the long-term optical background assumed by the old paradox had not yet formed. Stars appeared later, and individual stars do not shine forever. So the effective period of cosmic starlight is shorter than the total age of the universe. This is the main resolution: finite cosmic history, delayed star formation, finite stellar lives, and finite light travel time prevent the optical sky from accumulating an infinite depth of starlight. Darkness is not produced because distance defeats light. It exists because the luminous universe has not had infinite time to fill every direction. But expansion still matters, and this is where the answer becomes more interesting. As the universe expands, traveling light is stretched toward longer wavelengths. Picture a wave pattern painted on an elastic strip. Stretch the strip, and the spacing between the waves grows. The light arrives redder, with lower observed energy and intensity. Finite history switches off most of the distant lamps before their light can join the picture. Expansion adds another dimming and color stretching filter to the radiation that does arrive. In representative cosmological models studied by Overduin and Wesson, expansion can reduce the expected optical background by roughly a factor of 2 or 3. The estimate depends on the model and wavelength. But the larger conclusion is stable expansion deepens the darkness. While finite luminous history sets its basic scale, then the sky gives us a spectacular partial reward. The darkness between the stars is not physically empty. Human eyes detect only a narrow range of wavelengths. Instruments find backgrounds across radio, microwave, infrared, ultraviolet, X-ray, gamma ray, and other parts of the electromagnetic spectrum. The most famous all-sky background is ancient light, released when the universe became transparent roughly 380,000 years after the Big Bang. Expansion stretched that radiation into microwaves. COBE measured its spectrum as an almost perfect blackbody at approximately 2.725 Kelvin. So the sky is filled in every direction with ancient radiation, but human eyes cannot see it. A once hot cosmic image has been stretched and cooled until microwave instruments are needed to reveal it. The apparent blackness is partly a limitation of wavelength, not an absence of radiation. At this point, one dramatic explanation seems ready to take over. Maybe distant light fails because galaxies are receding faster than light. The phrase feels final. Nothing can move faster than light, so any galaxy crossing that boundary should disappear behind an unreachable wall. That must be why the sky is dark. Tiny problem cosmology is not describing a nearby object simply racing through space past a local observer. In general relativistic cosmology, the measured distance between remote regions can increase in such a way that a galaxy's cosmological recession rate exceeds the speed of light. This does not mean matter locally passes a nearby observer faster than light. More importantly, faster than light recession is not automatically the boundary of visibility. Tamara M. Davis and Charles H. Lineweaver clarified this confusion by separating boundaries often treated as identical. The Hubble sphere, the particle horizon, and the cosmic event horizon answer different questions. We can observe some galaxies whose recession rates were already greater than light speed when the photons now reaching us were emitted. Picture a swimmer in a changing river. At first, the current carries the swimmer away faster than the swimmer can move toward you. That sounds hopeless, But if the current changes during the journey, the swimmer may enter a region where progress becomes possible and eventually arrive. The river is only an analogy, not a map of space-time. The point is that the outcome depends on the complete journey, not one speed measured at one moment. Now the story splits into two problems that looked identical at the beginning. Olbers Paradox asks why the optical sky has not already accumulated enough radiation to appear covered by stellar surfaces. The horizon problem asks which signals emitted now, or in the future, can ever reach us in an expanding universe. Finite cosmic and stellar history is the main answer to the first problem. Expansion, redshift, and cosmic horizons reshape the second. That distinction changes what we are trying to solve. We are no longer searching for one wall that blocks all distant light. We are identifying which clock, wavelength shift, and horizon applies to each kind of darkness. There is, however, a genuine future limit. In 1998, two research teams studying distant Type 1a supernovae found evidence that cosmic expansion is accelerating. Those supernovae acted as standardized distant lamps, and their observed brightness and distance favored a universe that was not simply slowing down. If accelerated expansion continues in an appropriate form indefinitely, sufficiently remote regions can have an event horizon relationship with us. Light emitted after some point would never arrive, even if we waited without limit. But a true event horizon is not simply the place where recession calculation equals light speed. Think of a closing gate. Its speed at one instant does not tell you whether a traveler will ever pass through. You need to know the gate's entire future motion. In the same way, a cosmic event horizon depends on the universe's complete future expansion history. That future is not known with perfect certainty. Current evidence still favors an accelerating universe. A large supernova analysis, reported in June 2026, supported present-day acceleration, while DESI results have strengthened hints that dark energy may evolve with time. The acceleration remains supported. The long-term behavior of the dark energy associated with it is still unresolved. We know the cosmic vehicle is presently speeding up. We do not yet know whether the pressure on the accelerator will remain exactly the same forever. That uncertainty affects the detailed future horizon and the distant fate of visibility. It does not revive an eternal, static universe, and it does not overturn the stable answer to Olbers Paradox. So return to the original claim. Step outside at midnight in an eternal universe evenly filled with stars, and the darkness above you should not exist. That prediction was correct, only for a universe with a very specific combination of properties: infinite age, eternal stellar activity, static geometry, and unchanging light production. Our universe does not have that combination. It has a finite, observable history. Stars began shining after the beginning of cosmic history. They live for finite periods. Their light needs time to travel. Expansion stretches wavelengths, lowers observed intensity, and moves some ancient radiation beyond the range of human eyes. Accelerated expansion may also determine which future signals can ever reach us. But that is a separate boundary from the one that solves the classical paradox. The black gaps between the stars are therefore not directions containing nothing. They record missing time, stars that never existed, stars that did not shine forever, photons that have not had time to arrive, and radiation that reached us in wavelengths our eyes cannot detect. Darkness is not proof that the universe is empty. It is evidence that the universe has a history.